Okay, so here we go. Inclined planes. All right, so far, all of the problems that we've done have either been problems in which the object is being lifted and it's not on a surface, or the surface has been horizontal, and we did one problem where we had a thing being pushed against a wall where the surface was vertical, right? Obviously, in the real world, that doesn't always happen. Sometimes things are slanted or curved or whatever. Curved is a little bit more involved than we'll get to on the level of this course. But we should certainly be able to do what happens if a box is on a ramp. Okay? So we will call those inclined plane problems. All right? So in this one, we've got a 40 kilogram box that's being placed on a frictionless plane, and it is inclined at 30 degrees. And then our job is to find make a free body diagram and find the acceleration. So here's the deal with this. Point for me. Assuming no friction, which the problem tells us there isn't any friction, what direction is the box going to move? Well, down into the left, right? It's not going to go straight down because the ramp is in the way, right? So the ramp is going to kind of guide its motion, and the motion is going to be in a direction parallel to the ramp. All right? So far, all of the problems that we've solved, even if we've had to split it up into components, we've had a y component that went up and down, and an x component that went left or right. Okay? When you have an inclined plane, it sort of doesn't make sense to use those axes, right? Because the object isn't going to move along either the x or the y axis. It's going to move parallel to the ramp, right? And if you were to push it, suppose I was like, oh, I don't want that box to go down the ramp. If I was going to push it, odds are I would push it up the ramp. In other words, in a direction parallel to the ramp, right? And friction, if there's friction, which way is friction going to act? Either up or down the ramp, depending on which way the box is moving, right? So for that reason, what we're going to do is we're going to rotate our axes, okay? And instead of using an x and a y axis, we're going to use one axis that I always call it the parallel axis, and then another one that's the perpendicular axis, okay? So let's draw that in. So I'm going to do it in, I don't know, green, so we'll do it in blue. So, okay, so that dotted line that I just drew there is my perpendicular axis. Are you guys okay with the symbol for perpendicular? Little upside down T. All right, and then there's another axis that is the parallel axis. That is not the number 11, that is the symbol for parallel. All right, so it turns out, you guys, that in this problem, there are only two forces acting on the box. There are only two forces acting on the box. Gravity and there's no friction. It's frictionless. Normal force. Normal force. All right, now, this is something that I talked about when I gave you guys the definition of normal force, but it hasn't really come up that significantly yet. So right there's a box of wipes here sitting on the desk. Which way is the normal force there? Up, right? The other day we pushed the thing against the wall. Which way is the normal force now? This way, right? Okay, so do you guys remember I described to you how you know what direction the normal force is in? Do you guys remember? Ooh, say it again, Rondé. Oh, you're close. Perpendicular to the surface. The normal force always acts perpendicular to the surface. So for us, the normal force is going to go... Oh, shoot, I thought that was red. The normal force is going to go this way. Does that make sense? So we've got to figure out what that force is. And then the other force is gravity. Point for me. Which way does gravity pull? This way. Gravity doesn't go, oh, well, Mr. Hacker just put that thing on the ramp, so I'm going to help him out, and I'm going to point this way. Right? Gravity pulls stuff down. Always. All right? So my gravity is downward, and it turns out that these two vectors combined result in a net force that's down the ramp. All right? And we'll see that in a minute. Okay? So that's my technical free body diagram. And if it doesn't look like it, this force of gravity is meant to be vertical. It's supposed to go straight down. So let me pause for a minute. Are we okay with sort of what I've said? I haven't kind of done any math yet, but are we sort of okay with just the fact that these are the two forces? All right, so here's the main issue. One of our forces does not lie along the axes, right? Like yesterday, or whenever it was, the other day, we had this lawnmower, right? So in this problem, we had an x-axis and a y-axis, and so when Roy's force was at some weird angle, we had to find the x component and the y component, right? Okay, well, this time, instead of having an x and a y component, we're going to have, what are my two axes? Perpendicular and parallel. So I'm going to take this force of gravity and I'm going to split it up into two components. One of those components is going to be parallel to the ramp. That's the force that actually pulls the box down the ramp. And the other one is perpendicular to the ramp. That's the force that's canceled out by the normal force. Okay? So, I'm going to draw in the triangle, and some of you are going to want to kind of like turn your head sideways to kind of see what's going on. But, so here's my force of gravity, right? Oh, dang it. I wish that had not just happened. All right, so here's my force of gravity. Does that look vertical? Man, why can't I draw a vertical line today? There we go. All right, so here's my force of gravity. So what I'm going to do is I'm going to draw in a triangle where one of the sides is along the perpendicular axis and one of them is along the parallel axis. It doesn't really matter which way you go first, but based on the angle we were given, it makes more sense to start with the perpendicular one. So I'm going to draw this. This is my FG perpendicular. And then the other one is this. Please notice, this next line I'm going to draw is not horizontal. It is parallel to the ramp. And so here is my right angle. Yes.
Why would you not keep the axes like this and do the normal force?
Because we don't know what the normal force is, so it's really difficult to find the components of it. There's like too many unknowns, right? We don't know the only thing we would know there would be the angle. Okay? Whereas doing it this way, we know the force of gravity, or we find it very easily, and we know one of the angles in this triangle, this right triangle I just drew. Follow? So, very good question. Very good question. All right, so is everybody okay with a little drawing here? All right, so we're going to do a little bit of geometry here. Some of it's going to be kind of hand wavy, because once you do it once, it's always the same. All right. So the problem told us that the inclined plane is angled at 30 degrees. So that means that this angle here is 30 degrees. I'm really unhappy with this green pen. We'll do it in blue. So there's 30 degrees. So see the dotted blue line here? Wouldn't that also be inclined at 30 degrees? Right? So, and then the angle between the two blue lines is 90 degrees, right? By definition, they're perpendicular, right? So let's see. So I've got a 30 degree a 30, 60, 90 triangle. So that means that this angle up here is 60 degrees. Does that make sense? No? Speak up, you guys, if you're confused. I cheated and I moved it, which I probably should have. Let me do this. So there's a triangle formed by this blue dotted line. Here, I'll draw it in the green. Don't draw this. This will just help you see it. So, boom, boom, boom. Cool?
Yeah.
So, if this is 60 degrees, then what's this dude over here? 30 degrees. It's always going to be the same as whatever your angle is, whatever the angle of the ramp is. So this is the 30 degrees. Cool? All right, so let me undo all that just to kind of clean up the drawing a little bit. Now that's going to be annoying. Aha, okay. So it then turns out that this guy in here is also 30 degrees. Cool? All right, so there are three sides to my triangle, FG, FG parallel, FG perpendicular. Which one's the hypotenuse? FG, right? Because look, here's my right angle, right? So please don't think that just because these guys are slanty, that one of those has to be the hypotenuse. The hypotenuse is the one that goes straight down, and it's perpendicular, or it's across from the 90-degree angle. Good? All right, so that means opposite adjacent hypotenuse. That means the FG parallel is, assuming that the 30-degree angle is the one I want, is that one opposite or adjacent? Opposite. So to find the parallel component, you use sine. And to find the perpendicular one, you use cosine. And you've got those equations already written down here, right? Okay. Oh, there's a typo on the sheet, which I corrected here. So here's the equation to find the parallel component. You're just going to take whatever your force of gravity is and multiply it by the sine of the angle. All right? And then to find the perpendicular component, you use cosine. Here's the typo, though. I wrote parallel on both of them. I cut and pasted, and then forgot to change the word parallel to perpendicular. So make sure that your notes are corrected to say perpendicular here. Good. All right. So, is everybody okay with what we've got so far? All right, so let's take a second and find these, and I don't know whether we're going to have much time beyond that. So FG parallel is just FG cosine theta. So I guess somewhere I need to find FG, right? So my FG is going to be 40 kilograms times negative 9.8 meters a second squared, which gives you negative 392 newtons. Damn it, I just made the same mistake I told you guys not to make. And I just said damn it on film. Recording. I shouldn't swear. Okay. Okay. All right, so let's find it. So this is just going to be 392 times the sine of 30 degrees. Which gives us a number that I've written down, but let's just figure it out. 392 times the sine of 30. So you get, oh right, 196. And then similarly, you can find the perpendicular component by using cosine. And so that gives you, it's like 339 newtons. Notice I didn't do anything with my negatives there. I'm getting ahead of myself. Okay, so are we good? All right, give me one more second. The bell's going to ring in like 2 minutes. Let me just do this one thing. So here's your drawing. You're going to have a perpendicular component of gravity, which is negative 339 newtons. You're going to have a parallel component of gravity, which is negative 196 newtons. Point for me. Which way does it go? This way. That means it doesn't move sort of up or down off of the ramp. So what does my normal force have to be? 339, right? Oh, right. Okay, are we good? All right, cool. No homework tonight unless you need to go back and do the second half of 4-1. I apologize for not having those answers ready.